Welcome, everybody. Thanks for coming to today's tutorial. Today's tutorial is on network analysis made simple. It's a tutorial that has been long running since, I think, 2015, 7 years long thus far. We've updated. Myrtle in the back is my co-author for the tutorial. He is also one of the core developers of NetworkX, which is a core package that we use inside the tutorial for teaching network analysis and graph theory and applied network science and all that good stuff. So today, you basically have access to a core developer of NetworkX who can answer lots and lots of questions about NetworkX and network science as well. And I've been teaching this tutorial with Myrtle basically since my days in grad school, 2015 onwards. We've progressively updated the material. It is very much written from the standpoint of someone who did not understand network science in the past and needed to write teaching material to help learn network science, right? Learn by teaching is one of the ways that I have found to be the most effective for me to pick up anything new. So it's really written. We try to write this from the perspective of a relative beginner, right? Someone who doesn't really know network science, wants to get into network science, needs a little bit of help with the language and some grounding concepts, and then that forms your launch pad for exploring the wonderful world of applied network analysis and graph theory. So today, just now, we've tried to do a whole bunch of setup debugging issues. So I do want to raise a few things for all of you. So firstly, if you're not set up on any one of the three options that we have, that is binder, VS Code, local conda /venv installation, then raise your hand and Myrtle will come and help figure out the easiest way for you to get set up with the material. In order of priority, usually we would say go on binder because we don't want you to fiddle with local setup, right? That said, recently binder has been facing some financial constraints, and so we want to reserve binder's capacity, which is now limited, for those who really would struggle with getting set up on their local machine. So for today's tutorial, the order of priority is if you can get set up with VS Code Dockerized dev containers or with a conda environment locally, then that's preferable. But if you can't, then take the easy way out. Click on binder. If you get any issues on binder, basically the thing you need to do is refresh or open like network analysis made simple in incognito mode and refresh and refresh and refresh until it works. Trust me, that is the way that you get set up on binder. It is the proven way. Okay. Now, for those of you who are running the tutorial in binder, you'll want to know that there is a timeout. This is in order to not waste the reservation of compute resources on this public service, all right? So because there's a timeout, usually I would ask people to refresh or execute something inside binder every 5 to 10 minutes or so. Now, that's a little bit of a hassle, and in the spirit of automating anything that can be automated, today I learned from Myrtle a hack. Myrtle used to work on binder infrastructure as well. So here's the hack. I'm highlighting a bunch of code, which is right up on the screen. If you are on binder, put that inside a Jupyter notebook anywhere, and let it run in the background for the rest of the tutorial. That will guarantee that you never time out, all right? This is actually, if I remember correctly, what Myrtle said is that this is the official recommended. Is that? No, okay, I'm not supposed to say, no.
Sorry, could you say that again?
Sorry, that's Siri. Basically, do this so that you can keep the session running, and then, of course, out of courtesy for the rest of the binder universe of users, at the end of the tutorial, close your binder session so that the capacity can be freed up for other people. All right? Cool. Final note is there will be lots of exercises in this tutorial, so this is not going to be me lecturing for 3.5 hours. That would be incredibly boring. I don't think you'd want to hear my voice for 3.5 hours. With respect to the masking policy, I know that just like I mentioned just now, I know that some people need to read lips in order to listen effectively, like that's me. So when I'm in teaching mode, I will have my mask off and my glasses on. And when I'm in social mode, I will switch to glasses off, mask on. So basically, this will be the way that we handle today's tutorial for the masking policy. All right, and this is mostly just so that there's clarity of audio as well for the recording that goes up on YouTube. So what I mean by social mode is like if there's any error issues that show up with the code, you're having trouble with the exercises and you'd like a debug, you can raise your hand. Myrtle and I will come by and I will switch over to social mode to debug. Okay? Cool. Before we go on, can we just make sure everyone has one of the 3 ways of running code up and running locally? Like you're all okay? Thumbs up if you're good? Awesome, 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 awesome. This is great. Then I guess we can get started then. So today's tutorial is a tutorial that is on network science, graph theory, and network analysis more generally. And so at the beginning, what we probably would, what we should do at the beginning here is actually properly define what we mean by networks. And what I think is a very useful way of approaching a definition of a network is to actually first open up with a discussion on what we think are examples of networks, and then we'll introduce a very formal definition of them. So I'd like to open this time up to have you maybe either talk with your neighbor or think about it on your own. But I would like you to come up with, say, 2 or 3 examples of networks that are kind of categorically distinct, right? They're not like very similar things that you might encounter in your daily life, but they are like very distinct examples of networks. So I'd like you to talk with your neighbors or think about it on your own for a minute or 2, and then we'll come and discuss that together. Okie dokes. All right, let's regroup. I'd love to hear from all of you some examples that you all came up with of networks that you've encountered that you've seen before. Any volunteers? The highway system. Okay, can you describe what makes you think that is a network? All right. Yep. So cities are the nodes in this case then, and highways that connect cities are sort of the relations or the connectivity things that, the edges basically inside the graph. Cool. All right. Any other examples? Airline routes, nice. So what would you consider to be the nodes and what would you consider to be the edges? The airports? Flights moving from one airport to the next, that's right. And we have one more in the background. Social network websites, yes. Okay, so what would be nodes in there? Users are a node. Right. So you can have, if say, for example, on Twitter, someone follows another person, then there's an edge defined there, okay? Let's do 2 more. Any other examples? In the front?
It's like phone calls between different users.
Yes? Yes, that's right. So you have users are the nodes, and when they make a phone call to the next person, they have an edge between them. That's right. The pandemic. Right up my alley.
Contact tracing, trying to figure out who originally got sick, and connecting the edges and nodes.
Yes. So people in a contact tracing setting are the nodes, and whether they have had contact or not is one definition of the edge. Cool, right. So I think we all have a pretty good sense of, pretty good intuitive sense of what a network is. More formally, networks are comprised of 2 sets of objects. So please keep this in mind. This is like an extremely important definition that motivates a lot of the design decisions of how Network X and other graph packages are designed. There's always 2 sets of things. And by sets, we really mean mathematical definition of a set. That means You can only have unique items inside there. You don't have duplicate items, for example. All right? So that is the definition of a graph. Two sets of objects, one being the node set, and the other being the edge set. Right? Sometimes, colloquially, you'll get node list, edge list, right? And if you're not careful, it's easy to mistake node list, edge list for node set, edge set, and think that you can have like duplicate nodes inside the graph, but actually that's not correct. Every node is a unique entity inside a graph, and you cannot have duplicate nodes in a graph. Likewise, you cannot have duplicate edges in a graph. Your definition of an edge and your definition of a node are very precise in the graph. So when it comes to other examples of networks that we might encounter, I'm a computer plus biology person by training, and so I study proteins, more just generally speaking, and protein interaction networks are also an example. Protein interaction networks really do illuminate this problem of the specificity of the definition of stuff, right? When we think about proteins interacting with one another, there are many types of interactions that can occur. You can have things physically sticking to one another. That is one type of interaction. But you can also have a type of interaction where one protein does an enzymatic reaction that passes a molecule onto another protein, and that could also be considered an interaction of some kind. Now, what exactly is the definition of an interaction in this case? We have to be extremely precise, because otherwise our inferences about like what we're talking about become very imprecise as well. So now I want you to think, so in the spirit of getting practice about being very precise with our definitions, we're going to do another short discussion here, which is for the graphs that you've sort of examples that you've talked about with your neighbors, can you think of two things? One, how precise of a definition do you have to, can you come up with for the definition of a relationship between two nodes? That is the definition of an edge. And two, what are ways that you could be very imprecise about the definition? Right? So please go ahead, talk with your neighbor about that for a minute or two. All right. I see some of the discussion subsiding. So I'd like to hear again from all of you. For a given network example that you might have brought up previously, what would constitute a very precise definition of a relationship or an edge between two nodes, and what would constitute a very imprecise definition? Any volunteers? Yes?
So we are not sure. We're not sure if it's precise or precise.
Okay, let's bring it out and talk about it.
We're trying to think about, so we analyze retail data.
Retail data.
So between, obviously, our customers and retailers, and there's, so you could have the customer and the store be nodes, and then the transaction ID be an edge, and then depending on the amount of transactions that exist between that same customer and that same store, that could be the weight of the edge. But then there's also the product ID, which could also be a node itself. And so my brain just kind of breaks about that.
You're running into these objects called hypergraphs. So let's simplify things a little bit and focus only on like customer and store, right, as the two nodes types that are available. And one thing I like about the way that you've defined the edge is you're talking about in terms of a unique transaction identifier. Every transaction that happens between a customer and a store is a unique edge that exists between the node and the pairs of nodes, right? So this would, for the purposes of analyzing, for example, for the purposes of data modeling, right? This allows you to create a sort of relational table, right? Where you have one column being customer ID, and then next column being store ID, and the third column being a transaction ID, right? Or sorry, that in that table, the transaction ID itself is just like the indexer in that table, right? Exactly. And so for particular purposes where you want to analyze, for example, the volume of transactions between the distribution of volumes of transactions between a customer and a store, then that would be a very precise definition, right? But you can imagine situations in which if you're trying to drill down into the product level, then this becomes a very imprecise definition, right? Okay, so this is a really awesome example because what it's illuminated is the kind of question that you're asking defines how precise you need to be about the definition of the edge. If you wanted to go down to a product level, then you would have to rejig the configuration of the graph. I don't have an immediate way of rejigging the graph we brought up as an example in the moment, but there probably is a way to do it, right? So that is a very awesome example. Are there others that you can think of?
We're thinking of like the
Phone?
one person to another.
Yes.
We can't define it as like the person using the phone because you wouldn't know who that was. So it would have to be like the phone ID or the IMSI or whatever.
Yep.
And is it any contact between the two people or does it have to be like just a text message?
Yeah, that's right. So you could, if you, this depends on the kind of question you're asking of your data, right? So if you were to ask questions about like any kind of contact between people, text message and audio calls would be considered within like reasonable things to model inside your graph. But if you wanted to drill down more specifically into just the text messaging patterns, then having the definition of the edge being any kind of contact becomes too imprecise for answering that question. Okay, this is awesome. This is a very good example. Again, it shows how being precise or imprecise is very context dependent. You need to think through the logic of the exact thing you're trying to answer.
For that example as well, you might want directed links.
Yeah, I promise I did not plant this in you because this is the perfect segue into what's coming next, right? The kind of edge that, the directionality of an edge is also really important, right? So, and the directionality of an edge can be such that if you are interested in any kind of contact between people, you wouldn't bother with the directionality. However, if you were interested in how, say in a phone contact network, how people are, who is the instigator of the call versus who is the recipient of the call, and you're interested in that pattern of, say, information flow, right? Then modeling the directionality of that contact becomes really important, right? Cool. So in the Jupyter notebooks that we have on the tutorial repository, there are a few examples that are a little bit more pedestrian, I guess. Airport networks, social network, protein networks. The definition of the edge really, really depends on what kind of question you're answering. Now, I'm harping a lot on the definition of an edge because, as we'll see later on, through all of our examples that we'll see here, what makes a graph interesting is not the nodes. What makes a graph interesting is the edges. So if you get the edge definition precise, the kind of questions you can answer about graph data that you have also become very precise, okay? Cool. So when it comes to graphs, directionality is also really important. So if in a phone network you're interested in how information flows, that's one way to do it. If we were to take the very relatable example of a social network, right? In a social network, you have people who might be so-called connected to one another, but the underlying connection might be different. So in Facebook and LinkedIn, for example, or sorry, now what did they call it now? Meta, right? Or let's just use LinkedIn. I don't know tech. If we use LinkedIn as an example, right? Would we consider that the edge is between two LinkedIn users is directed, or undirected? Undirected, for what reason? Okay, right. And what about Twitter? It is directional, and the reason is?
Because I'm either following somebody or they're following me.
Right. You can follow someone and they don't have to necessarily follow you. So one thing that's cool about undirected graphs is the underlying, another way to think about undirected graphs is that they have automatic bidirectional edges, just as was mentioned in the back, right? So that is, again, like a modeling trick that you can keep in mind when you're thinking about graphs and the data structures that you build. Cool. So before we go on to actual programming, I want to really motivate this discussion about edges with this quote that I picked up while in grad school. This was, I think, 2015. I was in a seminar. It was at the Harvard School of Public Health. Professor John Quackenbush there. I forgot what he was talking about. I don't remember what his whole, like, what new Nature paper he was talking about. But I do remember a quote from his talk, and I jotted it down. The heart of a graph lies in its edges, not in its nodes. And what makes a graph interesting is the edges, the relationships between the nodes. The nodes basically are like, you can rethink of them as being entries in a table, right? Your user table gives you your nodes in a database. But the way they're connected makes the whole system interesting, right? And so this is really something that I want to convey through this tutorial. So with that, we're going to move on to the first notebook. We're going to go on to, we're going to go on to the second notebook, and this notebook is located in 01 Introduction, and its notebook name is 02 NetworkX Intro. What we're going to do here is do a very quick hands-on introduction to the NetworkX API. And the reason I think the NetworkX API is awesome for learning about network science is because the naming conventions of the algorithms and the methods, class methods inside there match up very closely with what you would see in the prevailing literature. And it is also a pure Python package, which means if you're interested in any of the algorithms, it's very accessible. You can peek inside the source code and see how exactly an algorithm is implemented. There's no translation, for example, to linear algebra land, which some graph algorithms can be implemented in terms of linear algebra. There's no translation there. You just think about nodes and edges, and you follow the logic of the code. At the same time, because it's pure Python, it's very easy to install. You don't really need to have too much else. It's for small graphs up to, I'd say about 100,000 to millions of nodes, right? Like this is relatively small in the world of like graph analytics, at least. For these small-sized graphs, NetworkX can comfortably handle the problem, even if it may not necessarily be in interactive time. You're at least not waiting for like months on end for things to run. All right? So yes?
So in the event that you're maybe running a Spark cluster, would this run, or would you need to like hack something around to get it to work?
You might need to hack something to work with Spark. Graph algorithms, by their very nature, sometimes involve, if you're familiar with order of complexity, some graph algorithms are O(n)(3) with the number of nodes, or exponential with the number of nodes. So it can get a little tricky. And the data model underneath being like pure Python dictionary-like things means I'm not sure how like distributing computation on of stuff on a graph might look like. So that would be something to explore on the side. That said, there are alternatives, right? Some graph algorithms have been implemented on GPUs, for example, with the cuGraph project by the Rapids team at NVIDIA. So that is another outlet if that algorithm that you're interested in is available on the GPU. Yes. If you look at one of the later advanced notebooks, which is 0.4 advanced and then 0.2 linalg. It does depend on some of the other content that is in the repo, but you'll see a comparison between like using network X methods versus using a linear algebra interpretation of the exact same method, and it's almost like 100-fold difference in speed. But then, of course, like the interpretation of the readability of that linalg thing is more difficult, so it's less easy to figure out what's going on inside there. All right, cool. So we're going to go on to the network X intro. Like I mentioned, it's an important one. And so I'm going to ask you all to do a few things. First off, let me see here. I'm going to restart my notebook, and we're going to run a few cells. And I want you to run cells up to this point where you see G is equal to cf.load 7th grader network, right? And that will just get the setup, notebook set up for us. So a key thing to note about the underlying data model of network X is that it's very dictionary-like, right? Dictionaries are built on top of sets, right? Sets are part of the core definition of graphs. Dictionaries allow us to have node maps to dictionary-like data structures, allow us to map node and edges to their properties that we might want to attach onto them as well. So the way that we create graphs and manipulate them is what we're going to see inside this notebook. So canonically, when you create a graph, you would do G is equal to nx.graph, networkx.graph. And if you wanted a directed graph, there are directed graph objects. If you wanted graphs which you had multiple edges between nodes, but each edge is like a unique edge, that is also possible, and there's multi-graph, so that's also a data structure that's available. And then key to the data structure, the graph data structure in network X is g.nodes and g.edges. G.nodes lets you access the nodes that are present in a graph, and g.edges allows you to access the edges that are in the graph. Okay? So to keep things concrete and less abstract, what we're going to do here is we're going to load in an example graph that has already been created, so you don't have to worry about how it was created just yet. And we're going to try to do a few things where we manipulate the graph and query the graph for information. So this is this graph that we're going to load is a study of 7th grade students in Victoria, I believe, Australia, not British Columbia, my hometown. So, in this graph, what the data that we're modeling is as follows. These students were asked on 3 separate occasions to nominate their preferred classmates for those respective activities, right? So you could, as a student, nominate 3 or 5 or 15 people as your preferred, preferred partners in different activities. Every node, therefore, is defined as a student, and every edge is defined as they have had 1 or more times where they've shown a preference for the other student, all right? So let's just do a quick pulse check here. Is this directional or undirected? Directional, exactly. This is not a trick question at all. Okay, cool. And then the edge weights will run between 1 and 3, right? So we have metadata that's stored on the edge that says this student prefers that student 1 time, 2 time, or 3 times, right? Cool. Now, in the original data set, this was taken from an all-boys school. What I've done here is modified the data set for some visualization purposes later on so that we can look at different node categories. So we have the data set modified to come from a mixed gender school, right? So you have boys and girls both inside the data set. So now what we're going to do is we're going to start by querying the graph for key information that is stored in the graph. So the first one is to know what is the type of the graph. So in Python, if you do type of G, it will show you that this is a directed graph. So we've instantiated the graph object as an nx.dieGraph, directed graph, and this will be reflected in its type. By contrast, if you did nx.graph alone to create the graph object, you would get .classes.graph.graph without the di inside there, okay? So if you run those two cells, you'll see that. So the next thing we're going to do is we're going to take a look at one thing that's really important when you get a graph is you want to know what nodes are present inside that graph, okay? So one way to do that is to, I'm going to comment this out and type this for you guys. G.nodes, right? If you do G.nodes and you run the cell locally on your Jupyter sessions, you notice that what you get returned is this thing called a node view object, right? It is an immutable view of the nodes that are present in the graph. You can still add and remove nodes in the graph, but you just can't manipulate the graph by looking at G.nodes, okay? So this is an important concept. One thing that is true about the G.nodes thing is I don't believe it is subscriptable, because if you think about the definition of a set, you can't slice a set because it is inherently unordered. So if you were to try this with me, G.node 0 to 5, you should get an error, right? And this again reinforces the very strict mathematical definition of a graph, right? So if you do want to like obtain a subset of nodes, what you would want to do is cast G.nodes inside a list and then slice into it afterwards, all right? How are we doing so far? So far, so good? Feeling okay? Shouldn't be too difficult up to this point, with maybe the exception of you can't slice into G.nodes, right? Like that's the only sort of gotcha that makes sense once you think again about the definition of the node set rather than a node list, okay? So one thing that you can do with G.nodes is you can check how many nodes are present inside the graph. So if you do len of G.nodes, you'll get 29 over here. And here's a really cool thing. If there is metadata that is attached on top of each node, you can do G.nodes data equals true, and you'll get back this data structure. Okay, so let's kind of do a quick Python check here. What is the data structure, if we were to describe this in words, what is the data structure of this like list of things? This is a list of tuples of length 2, in which the first element is the node ID, and the second element is a metadata dictionary that maps key value pairs that are metadata attached to the node, right? So far, so good? Okay, cool. Yes?
That doesn't return the 1 to 3 that we put the, these are the nodes, not the edges. Ignore them.
That's right. These are the nodes. We'll get to the edges soon. We can also select out individual nodes, right? So if we run G.nodes of 1, what we'll get back is the dictionary of metadata that is associated with that node 1, all right? So you might be wondering at this point, like, what, do nodes have to be integers? Actually, no. They only, strictly speaking, have to be hashable things. So you can't make a list a node because lists are not hashable, but you can make a tuple a node because tuples are hashable, right? So that is possible. But for most applications, I would say that most people would use strings as nodes just because they are human readable, easily identifiable. So when you do G.nodes and you look at what nodes are present, like it's very obvious what the nodes are. When I played around with genome graphs at work, in there, every position, comma, letter pair, right, is a node. So you can actually represent that by a tuple in which you have the first element being the position in a sequence and the letter of the nucleotide or protein sequence being the letter, the second element. And that was sort of the data structure that was used to represent this so-called genome graph, right? And I can explain genome graphs in like a different setting. I won't go into over there, but I just want to make the point that anything that is hashable is doable as a node, right? If you play around with an API later, you can do that too. Cool. Now, because the node data view with data equals true, that's dictionary-like. So you can actually loop over it as if you were doing for key value in dictionary.items, right? In this case, you would do for node, comma, data in g.nodes, data equals true. Now you have access to every node with its corresponding metadata dictionary. So this then brings us to the first exercise of today, which is to count the number of boys and girls that are present inside this data set, right? So I'd like you to attempt this exercise. Feel free to talk with whoever's your neighbor in this like lattice graph of people who are sitting in the tutorial room. Feel free to talk with your neighbor, and we'll spend about a minute or two just to work on this exercise. While you all are doing it, I'm going to try to implement the answer from memory. I have it all at the bottom of the notebook, but this is a great way for me to pace myself. Why is the output collapsed? There we go. Okay, so given the lack of specificity in the phrasing of the task, you could probably find other creative ways of counting the number of males or females that are in the data set, in the graph. I use collections.counter. You don't have to. You can do it your own way. But as long as you figure out that there are 12 boys and 17 girls inside the data set, you're pretty much on track. A loop. Ah, OK, that works too. So just to do a quick pulse check, how many of you feel OK with this exercise or would like a little bit, if you feel OK, give me a thumbs up. If you'd like a little bit more time, then raise your hand or something. Or I should have put like sticky notes. There's a very nice and discreet way of doing this. If you're struggling, you put a red sticky note on your laptop. If you're not struggling, then you put a yellow sticky note on your laptop. I should have done that. Cool. So in the interest of time, we'll move on, but hopefully this is a good exercise that shows you how you can query the metadata that is on the node set, right, of the graph, and use that to derive summary statistics about the node set. Down below, I have this thing here, which is about testing, right? So this is sort of a side point, but as a practicing computational/data scientist, we run into data quality issues all the time, especially in my realm of not like highly structured streaming data, but actually wet lab scientist generated data. We have lots of potential data quality issues. So there's this practice that I've started to engage in, which is to test data that comes in and validate all the data that comes in, that they fit the assumptions that I believe that they should fit. And so leveraging test functions like this throughout the code base is one way of doing it. There are other tooling for, like, say, Pandas data frames. There's Pandera and Great Expectations that let you validate your data on the fly. But as basically, this for me is like a defensive programming way of operating, and it has saved my posterior many, many times when I'm doing my analysis work. Cool. So now we queried node information. Let's also query edge information. So analogous to g.nodes, you can do g.edges, and that will give you an edge view. Again, just like the node view, this is an immutable data structure. You can't modify this guy and therefore modify the underlying graph. There are explicit methods for this. So you can do that. Again, this is an edge set, so you can't index, you can't slice directly into it. This will be out edge view does not support slicing, so it fits the definition of edge set. But there is a very helpful error message put over here, which suggests exactly what to do next, which is to do list of g.edges, which is exactly what the original was all about, right? So if you do list of g.edges, I believe you actually don't need the parentheses either. That also works. Same should apply for the nodes as well. If you do list of g.edges, you'll get back a sliceable data structure, okay? At the same time, you can do len of g.edges to get the number of edges that are present, and just as with g.nodes, you can pass data equals true and get back the metadata that's associated. So likewise over here, you can also get back the metadata that's associated with every single edge. So then, again, this is not a trick question. What is this data structure? This is a list of tuples of length 3, in which the first element is one of the nodes in the edge. First node in the edge, that's right. The second element is the other node in the edge. And then the third element is the dictionary of metadata that are present, okay? You can also select out individual edges. Now, the way that this syntax works is kind of nice. You actually do the square bracket selector syntax, and then you do node 1, comma, node 2. It used to be g.edges and then select node 1 and then select node 2, but this, in my opinion, is actually a little bit saner of a syntax. So it was recently added. So you do g.edges 15, comma 10, you'll get back the metadata that's associated with the edge between node 15 and node 10. All right, question?
So when the graph is not directed, can you swap those indices and you'll still get that?
Yes, so the question is, when the graph is not directed, can you swap the indices and still be a valid edge? The answer is yes. So in an undirected graph, the left, comma, right order does not matter. In a directed graph, the left, comma, right order absolutely matters. In a directed graph, left is the source, right is the sink. So 15 to 10 means student 15 nominated student 10, in this case, twice for their activity, right? So that is a very good question. You'll get a key error if an edge does not exist. So this, obviously, we won't run. And just as it is with g.nodes, where you have an iterable of 3 tuples, same thing happens over here. So you have n1, n2, d as your loop variables if you were to loop over g.edges data equals true, okay? So what we're going to do next is another exercise, summarize the edge metadata. Actually, sorry, it's verify that the maximum number of times that we've recorded for count is 3, right? Like this is, again, a data validation check on the graph. So let's attempt that exercise. And when you're done, feel free to give me a thumbs up. By the way, I forgot to mention at the beginning, if we're running too slow for you and you want to just speed ahead and do all the exercises below on your own time, I'm completely unoffended. Like, please do it. Not a problem, okay? Give like... Yeah, exactly. We actually do have enough material for a 6-hour tutorial, which would be extremely tiring for everybody. But as you can see, there's been a lot of time put into this guy. So cool. I have the following implementation on the screen. Basically loop over this g.edges with data equals true, append count, and then get its max. If you look at the official answer, there's actually a compact list comprehension that is used inside there as well, right? So multiple ways of addressing the same problem. And likewise over here, we can test to make sure that the answer is correct. Once again, this is a sort of data validation check, right? Cool. So now we know how to query a graph object. The next thing that we want to do is know how to manipulate it. So you can create a graph, G equals nx.graph, and now you have an empty graph with no nodes and no edges. Or you might have a graph that someone gave you. In this case, the graph that we have over here, the G is equal to nx.digraph with a whole bunch of nodes and edges already present inside there. How do you add nodes and how do you add edges? And correspondingly, you can ask the question, how do you remove nodes and remove edges or modify nodes and their metadata and properties? So what we're going to do is focus only on just adding nodes. There are corresponding methods for removing nodes as well. So this is what we're going to be doing over here. So if you want to add a node into a graph, you do g.addNode. And what you do is the first argument is the hashable entity that represents the node. And every keyword argument that follows automatically gets collected and squashed into a metadata dictionary entry that gets attached to the node. All right? So literally, if we did g.addNode of this node with the keyword argument node data 1 equals something over there, then that node will have in the metadata dictionary node data 1, string node data 1 as the key, right? And the value will be this some value thing over here. And then if you add in a second one, which is node data 2, then literally in the metadata dictionary, string of node underscore data 2 is the key that becomes part of its metadata. And it will be assigned whatever value that is. It will map to whatever value that is over here. Question? That's right. That's right. So this is one of the ways that you have, this is where NetworkX's flexibility is really shown. Of course, we know that when you have flexibility, you have a lot of power, which means you could end up misspelling something and accidentally adding the wrong key, which for FYI has happened to me as well, right? So take a lesson. You can, if it happens to you, just know that more experienced people have also suffered the same fate as well. As we'll see later on, there are ways to load tables, like pandas data frames, into a graph. And that provides a nice structured way of avoiding a lot of typographical errors that might show up. So that's an alternative you could think about. So we have add node. Same thing happens for add edge. The only difference here is you have node 1, comma node 2. So the first two positional arguments are the nodes that are present inside that edge. And then edge data 1, edge data 2 become literal keys in the metadata dictionary. Question? That's a really good question. You can add nodes into a graph by just doing g.addEdge. That is doable. That is allowable. And I forgot what the rationale is for that design decision, but if I were to imagine what it was, sometimes you're provided with an edge list and not the node list. So the convenient way to add in nodes into the graph is to loop over that edge table that you might be given and just automatically add in a whole bunch of nodes while you're at it. Okay, good question. Anything else? All right, cool. So what we're going to do is embark on this exercise down below. In this exercise, we're going to figure out that we've left 2 students out of this network. There are student number 30 and student number 31. One of them is a male student, the other is a female student, so you want to add that information into the graph. And they love hanging out with one another, and they love hanging out with student number 7 as well, right? So the way that we express that they love hanging out with one another is that we set their edge attribute count equals 3 on the graph. So I'd like you to go ahead and add this information onto the graph. You've seen the necessary APIs that are needed to make this happen. So spend about 2 minutes or so, and then once we're done with that, we can actually take a quick break. Okay, can I just quickly check how many of you have added both nodes and added at least 2 of those edges? Okay, cool. We can move on. This is mostly in the interest of time. I know how tedious it can be if you want to manually add edges inside the graph, which is the way that the official answer does. So as long as you get the idea that you can do g.addNode something, g.addNode something, with the metadata attached to it, same for the edges, you're good. The other key thing to remember is that this is a directed graph, not an undirected graph. So if you want to add the bidirectional nature, you actually have to explicitly add in the reverse, right? So if I add in node 30 to 31, I also need to add 31 to 30. That is important because that is the specification of what was inside the exercise, right? They love hanging out with one another. So there's no way out of this one. Cool. Any questions on this so far? At this year's ODSC, I got a question about like, oh, but what if I need to add like a whole bunch of nodes? Do I really have to do this all the way? Not really. You can write a for loop if you have a prepared data structure that you can loop over. You can then call g.addEdge, g.addNode, right, inside there as well. Okay. And if you are really curious, go to the NAMS directory, then go to solutions, and then go to, not solutions. Go to loaddata.py, and you will see how a lot of these edges, these graphs are created, and they give you an example of how you can like create graph objects from predefined text files, CSV files, et cetera, et cetera. All right? Cool. So we're gonna move on real quick. I have another test here, not so important. If you get the idea of, what do you call, data integrity tests, then write these for yourself all over the place. They're very, very handy. At the bottom are some coding patterns that we have over here. As I mentioned, some of the official answers inside the repo use list comprehensions. That is also very idiomatic. The most important thing, though, is that you can loop over g.edges and g.nodes. And as long as you know how to expand the tuple of loop variables, then you're in a good spot. All right? So in this case, we can do if we do g.nodes, we can expand the loop variable tuple into like n comma d. And if we're doing g.edges with data equals true, then we can expand the loop tuple variable into n1, n2, d, and access all of that information in an idiomatic fashion. All right, so with that, we're going to pause for 5 minutes. We finished at 10 a.m. So this first section of the tutorial at 10 a.m., so that's awesome. Let's pause for a 5-minute bio break and reconvene at 10:05. And I'm going to go back into social mode. No, I think we can keep the recording going. I believe the post editing is when they might cut out the breaks or something.
I couldn't find the email you sent for
Setup?
setup, yeah.
Ah, okay.
So did you miss my email or what?
Oh, you sent an email?
No, everybody said they get an email,
Ah,
but I didn't receive any email.
I sent it through the official tutorial, like PyCon messaging system, about last week. So did you register for the tutorial after?
I think so.
Recently?
Because
Okay.
I registered like 2 days ago.
Ah, okay, that explains it. Okay, so for setup, let me see here.
Can you forward that email to me? Or?
I don't have a way of forwarding the email specific. Oh, hold on, I might actually. Okay, middle can help you with that. And I'm going to get some coffee myself. I'll mute myself. All right, I'm back in teaching mode. Almost. Missing this. There we go. Now I can see everybody clearly. I found that after a whole year and a half of just like staring at my computer screen, my eyesight has just gotten worse. It's happened. Pardon me? This one has, but usually because it's close enough, I don't have it on. So it's taken a toll on my eyesight. Alrighty, so we're a little bit over, but that's okay. Let's get started. One thing that often comes up is as an early sort of question when dealing with graphs is, how do I visualize it, right? Visualizing a graph helps you sanity check that the graph was constructed correctly. I remember in my early days of using NetworkX, I would be incredibly confused because I would manipulate the graph, but I had no, as we saw in Notebook 02, NetworkX intro, but I had no way of figuring out, did I do it right? Like, what's interesting? Can I just see it? And one of the early frustrations that I encountered was that I was mixing up the visualization of a graph with the construction of the abstract sort of graph object in computer memory, right? It's really important that this be clarified, right? Like when you create a graph and you manipulate it in memory, there is a way to turn that into circles and lines in a Matplotlib canvas, but until you explicitly call for that, we're actually just dealing with a thing in memory, in abstract. We're modeling relations, we're modeling entities and their relationships, but we're not yet going to see them, all right? So what this notebook here is all about, how do we visualize graphs? So what I'm going to do with this notebook is, it's not going to be as interactive. It's going to be a very, very short, quick lecture, probably 10 to 15 minutes tops. I'm going to have you all run the notebook from top to bottom. So you should, if you're in Jupyter Lab, there's this like fast forward icon that you can click. It'll restart the kernel and then run everything. That's one way to do it. If you're in VS Code, there's a run all button at the top that I'm mousing over on my screen over here, right there. So you can click on that guy, and they'll produce all of the visualizations. But I do want to talk about visualizations because I've seen some pretty bad, complicated, horrible hairballs, and I want to encourage people to get away from hairballs. That's basically the whole message of this notebook. If you've seen how a certain subclass of physicists who study the internet make their diagrams of the internet, you might see something that looks analogous to what you see on the screen here. That is, you see a bunch of circles that are separated in this laid out according to some physics-based, force-directed algorithm that puts stuff that are highly connected to each other, clumped up, and puts stuff that are poorly connected out on the periphery. It is indeed one way of visualizing graphs, but as you can see with this graph that came from the previous notebook, this is going to very easily turn into a hairball, especially as you go to more and more nodes and more connections inside the graph. So how do we deal with this problem, right? Like that is a problem if you want to use a visualization of a graph to help you either understand something about the structure of the graph or to communicate some idea about the graph. What's even worse actually is that hairballs are initialized oftentimes with a random seed. So unless you explicitly remember to control the random seed, you will not get a reproducible figure, right? Your node layout will always look slightly different. So yeah, hairballs. This graph has like 28 nodes. It already looks like a hairball. So imagine what happens when you go to 200 nodes. It's going to look even worse, right? So there are ways to visualize graphs in such a way that you can derive insights and communicate effectively using those visualizations without resorting to hairballs. My whole message of this notebook is let's avoid hairballs and think carefully about how we design rational graph visualizations. So here's one way that we can visualize the network. This is done by creating a matrix plot, all right? So let me explain a little bit about the matrix plot. On the, just to check with the camera, if I move over to the screen and start pointing, that's totally captured inside the video, right? Okay, awesome. So in the matrix plot, what you do is you actually lay out the nodes and on the x and y axes of the matrix, and then you fill in an entry between every pair of nodes, depending on whether an edge exists between them or not. In a directed graph, you'll have to define carefully what is the source and what is the sink. So you can, for example, put the source on the x-axis and the sink on the y-axis, and that is totally fine. Or you can swap the two around, and that's totally fine too. But where you fill in the edge over here will depend on your definition of source and sink, all right? Now, immediately, what's visible from this graph is that the entries in this matrix are asymmetric. Does this make sense for a directed graph? It does, right? Because you can have an edge going from one to the other, but not the other way around. And by contrast, if you were to have a symmetric matrix plot, then you would know immediately that this graph was undirected or can be modeled as an undirected graph. So already, the type of the graph is easily visualizable from just this plot. In addition to that, you can do other things when you prioritize the position of the nodes and by, for example, grouping the nodes according to some category that you have. So in this case, we have the male and female nodes separated out with one another. You might even be able to do some other cool things, like ordering. If we had the information, we could order the nodes according to their birthday in the calendar year and figure out if there were some sub-patterns that we weren't picking up. Okay, you're back. Come back. We could be able to do that and see if there were certain patterns in the edges that were induced from this ordering of nodes down at the bottom, right? So key lesson over here is if you want to draw your graphs in a rational fashion, you really want to prioritize the position of the nodes. If you can prioritize them by grouping, ordering, and laying them out in some fashion, then your graph visualization immediately yields some useful insights. Okay, any questions?
So for having a data set where you don't have one of those orderings and you want to like make a look at compare a graph from like last month to this month, can you create an artificial partial ordering like precede or something?
Yes. So let's say you have a graph data set that is in which every month you have a slightly different configuration of the graph. One way to visualize this is to ensure, first off, that you include nodes you ensure that the node set is constant from month to month to month, even if it isn't connected in one of the months. You order them in exactly the same way from month to month to month, and then you only change, the only thing that becomes different are the entries in the matrix in this example, right? And then you can see how you can like almost imagine creating a PowerPoint deck where you flip through the slides, and each slide has one of these matrix plots. And because the node set is kept constant, all you're seeing is the difference in the structure from slide to slide to slide to slide, right? So it becomes very useful for communication. Any other questions here? So I want to raise one other point. The fact that we can do a matrix plot already hints at the connections between graphs and linear algebra, right? Because there is this linear algebra data structure, linear algebra-based data structure called the adjacency matrix, which can be weighted or simply binary, that records which nodes are connected to which other nodes, right? You can imagine a two-dimensional matrix of numbers to represent that, okay? Cool. Yeah. There's one other really obvious thing in this graph. What do you notice about the diagonals? Yes, I saw the arm. The diagonals have nothing inside there, right? Which is kind of nice, right? You're not raising a generation of narcissists who are, okay, so I'm not going to go down that 1940s quote from World War II. Oh, yeah, that's right. Exactly. You can also take a look at like inter versus intra-node sort of connectivity over here, just by simply grouping your nodes in a sane fashion. Cool, awesome. So here's an alternative visualization. It's called the arc plot. And the way that the arc plot is drawn is you group and order your nodes on the x-axis over here. And all you do is draw circular arcs between anything that is connected. All right? That is one possible thing that you could draw. Right? And if there were, say, for example, if the x-axis was time-based and you saw a lot of large arcs, you would know that people are connected far in time. Whereas if you only saw very local arcs, you would know that your nodes are very locally connected in time, right? So that is another visual insight that is possible from the graph. The third one is the Circos plot. And all this is you take the ends of the arc plot and you join them together, and you draw nice little arcs inside there as well. Circos plots are actually the first thing that I encountered when it came to nicer graph visualizations. They really enable you to visualize lots of groups of nodes together and how they're connected. I encountered them. The most memorable example that I can think of is in either a science or a nature paper where there was an analysis of the migration of humans throughout natural history and how genomes from continents were connected based on sort of migration patterns and similarity of gene content, right? So that was another really cool example. Now, of course, that one involved a lot of custom graph stuff that had to happen. So the implementation here is not as scalable as what would be needed for that level of detail. But that was still a very, very cool thing. The final one that I want to show is the Hive plot. Oops, sorry. Let me see if I can zoom out on this guy a little bit. There we go. That's exactly what I wanted. Okay, so with a Hive plot, what you do is you take your group of nodes, up to 3 groups per hive, and you split them out onto different axes. One axis is for one group. So if you had 3 groups over here, you would have like a 12 o'clock, 4 o'clock, 8 o'clock sort of positioning of your axes. What's really cool here is you can actually clone the axes, and as a result of that, visualize the intra-group and inter-group connections separately. This is another one of those really cool visualizations. Both the Hive plot and the Circos plot, I picked these up from a series of articles written by Martin Kraswinski, who is at the British Columbia Cancer Research Center as a research scientist / visualization scientist. And he had a lot of really good articles, and I was curious about it, so I started making my own implementations of Circos and Hive plots in Python, built on top of Matplotlib, because the tooling back in 2014 for making this stuff was all in Perl, and I didn't know Perl. I knew enough of Python to be dangerous, to try to implement these on my own. And so these plots are inside a Python package that I've built and had many contributions from other people. The API has evolved quite a little bit over time. It's called NXViz. It's a graph visualization package that works explicitly with NetworkX graph objects. Its intent is to be its intent is to be this sort of research, like my part-time, very, very, very much part-time research into graph viz and sort of figuring out what are rational ways of graph visualization. But I also do use the package at moments at work for when I need to put up a visualization and do some sort of a communication about like what exactly is inside a graph that I'm talking about in a scientific presentation. So it does come in handy for so-called scientific communication uses as well. If you're curious about it, there I think are links inside the notebook to NXViz. There's an API documentation outside on GitHub pages as well. And its API is very much trying to be like Seaborn, where it's declarative, it's not very imperative, and it's also has a few flavors of ggplot where you sort of compose in annotations on top, but it's all done in a way that's compatible with matplotlib. Question?
With the art plot, is there an option to like in-group connections? Maybe go at the bottom and maybe cross-group connections are at the top?
I'd have to see. I forgot whether that's possible in the implementation. Might be able to do that. I'd have to double check. Yeah.
With these plots, can you select a node and pull on it?
No, this is matplotlib based. There have been requests to make this compatible with HV plot, which is built on top of Bokeh. I just haven't had the bandwidth myself to write the layout algorithms. Sorry, I haven't had the bandwidth to execute on that. I think the layout algorithms, the node layout and edge drawing algorithms are all back-end agnostic, but it's just getting the thing onto a canvas, which I haven't had the time to do.
I've already answered this, but with the edges on these plots and then the nodes on the adjacency matrix, can you color those by weight?
Sorry? By weight. Yes, actually, so the recommended way for handling weights, in my opinion, personal opinion, is to use transparency. And if you have a way of mapping your weight scale to 0, 1, then you have a very clear path. The alternative, of course, is if you can categorize your weights, continuous weights, into discrete bins, they make for a little bit easier visualizations. But of course, you trade off the sort of nuance, right, in the weights. Yeah, so that is something to keep in mind. Was there any other questions? Okay. So if not, I'm going to leave you with this. I'm going to leave this notebook with you with sort of just one key idea. That is, you should prioritize the placement of your nodes. Think really hard and carefully about how you want to prioritize the placement of your nodes. If you do that, then you will find that your graph visualizations become much easier to talk about and communicate when you're in a real setting, right? Like the hairball just doesn't cut it anymore, right? This is 2022, sorry. Why am I still living in 2021? Gosh, this is 2022, right? So we got to move graph viz into a more modern direction. All right, so if we're cool on this front, we're going to move on to some of the more exciting things, the things that really highlight how the structure of the graph gives rise to the important features, important parts of the graph. So what I'd like you to do is open up Notebook 02 algorithms, and we're going to walk through, hopefully we can make it through Notebooks 1 to 3 over the next hour. We will break at 11 for another bio break, but by 11:30, I'm hopeful we should be able to finish all 3 notebooks together, okay? So let's get started over here. This notebook is all about figuring out which nodes in a graph are important. Now, as you probably can intuit, if you have a graph where someone is connected to many people, right, that person might be a really important person. And that's kind of the core idea that we'll hint at today. So the graph that we're going to load is called the social patterns data set, and this text describes exactly what that data set is. Basically, there's an exhibit. It is an exhibit on infectious diseases Just to clarify, this is not a contact tracing data set, right? This is not one where we're actually trying to figure out who spread the germs to the next, spread a virus to the next person. This is instead a data set that is asking, did two people have face-to-face contact for more than 20 seconds inside this gallery exhibit? And it's, for simplicity, what I have done here is I have actually only taken, you can have multiple contacts, right, between people over time. For simplicity, I have only taken the last contact between people. And so just a sanity check, in this case, is the data model of a directed graph or an undirected graph a little bit more appropriate? Undirected, right? And for the reason probably that if I have face-to-face contact with you for 20 seconds, you automatically have face-to-face contact with me for 20 seconds. It's kind of an automatic bidirectional. So let's go ahead and run this cell down here. We can also verify that this graph is an undirected graph. It is implemented as an undirected graph, so we never have to worry about the directionality when we access graph edge information. And as always, when you get a graph object, make sure you know how many nodes and edges are present. Okay, so when it comes to figuring out what's an important node in a graph, one metric that can be used is the number of neighbors that the node has. Neighbors has a very specific definition that comes from the edge structure in a graph. That is to say, if a node is connected to another node, they have an edge between each other, then they are neighbors of one another. Okay? So NetworkX has, in the Graph API, you can do g.neighbors of a particular node that is present inside the graph. And what you'll get here is actually a kind of generator that doesn't immediately return the exact neighbors list. But what we can do over here is cast g.neighbors of 7 into a list. Now, you can imagine some of the design decisions that are being made in NetworkX here. Some nodes may have 1,000,000 connections. If you were to return the list straight away, that would get pretty bad. So having an iterator, a generator basically, over the neighbors is sometimes a saner, in this case I think a saner design decision than to immediately return the list for you. In this case we're dealing with nodes, a graph in which nodes don't have on the order of 10 to the 6 connections, edges, right, in which they're participating in, so we're okay to just do list of g.neighbors here. So one of the things I'd like you to do then, right, now that you know how to query a graph for the number, for its neighbors, what I'd like you to try out over here is to create a ranked list of nodes based on how many neighbors they have, right? So spend about maybe 5 minutes, 3 to 5 minutes on this exercise. And I would encourage you to pair program with your neighbor because this is a really great way of like sharing knowledge. Okay, so I'm going to very quickly run through my own solution. It does rely on pandas, which I believe is maybe a modern Python idiomatic way of handling the problem. The first time I implemented the solution, I used sorted with Lambda functions, and that felt really clunky, and lots of people were like, what? What are you doing here, right? So I think pandas makes this problem a little easier to handle. The first thing that, in order to solve this problem, that is to rank order nodes, the first thing that we need is a mapping from node ID to the number of neighbors that it has. So that is what this first 3 lines, 7, 8, and 9, in the code block are intended to do. That is to map node to the number of neighbors that it has. So we create a dictionary over here. Once we have a dictionary, every dictionary can be cast into a panda series. The keys become the index, and the values become the values inside the panda series. So if we do pd.series, sorry, let me comment stuff out first and walk you through it neighbors mapping over here looks like a dictionary, right? So key value pairs. Then what happens afterwards, we cast this as a pandas series. The index is the node ID, and the number of neighbors is on the value inside the pandas series. And if we add in a sort values over here, then the first row in this series, first entry in this series, will be the node that has the most number of neighbors. And you should get node 51, followed by node 272, followed by node 235, et cetera, right? So that's sort of the answer here. If you want to look at what the original solution looked like, it looked like this, right? And you can imagine why people are going like, what? What are you doing here, right? So it involves anonymous Lambda functions and the likes, and not really the most learner-friendly implementation. There's also one that is like a generator-based way of handling the problem. I have friends who looked at the repo and were like, yeah, this could be solved with generators. And then they went and solved it with generators. And then I looked at their answer and went, what? What are you doing, right? So, but in my case, now that we have pandas as a fairly idiomatic, well-known package, it feels right, sensible to depend on pandas and use its data structures and methods as much as possible. Okay, so let's think about neighbors. A small graph that has 15 nodes, right? How many, if I'm a node inside that graph, how many possible neighbors could I have? 14 if? Sorry. What conditions would it be 14 and not 15? Almost there. The key question is whether you are allowed to be connected to yourself. There's this concept of self loops. I didn't introduce this before, my apologies, but this is a very key idea, right? If you are a node in a graph, the total number of nodes that you could possibly be connected to is either n minus 1, where n is the total number of nodes in the graph minus yourself, under the condition that you can't be connected to yourself, or it'll be n, which is all of the nodes, under the condition that you are allowed to be connected to yourself, right? That's a very important thing to keep in mind. Okay, so this node in a small graph has 14 neighbors out of 14 possible neighbors. This other node in another graph has 478 neighbors out of a total possible of 650 neighbors. In each graph, which node is more, when you compare the two graphs, are we able to use neighbors, do you think, to make a statement about which node is more important? How so? Well, the node in the bigger graph has more neighbors. So is the node in the bigger graph? Relative to the size of the graph, yes, exactly. So this is where we're going to go into the next idea here, where we're not talking about simply the number of neighbors that a node has, but rather what we call the degree centrality metric. That is to say, how important is a node given its broader graph context while factoring in the number of neighbors that it has as well. So in this case, a node that has 14 neighbors out of 14 possible neighbors would be really important in that small graph. And if you were to rank that node against the other one that had 450 neighbors out of a possible 600, you might even say that this node in the small graph is actually more important for the small graph compared to that node in the bigger graph, right? That's what this centrality metric is all about. So the concept that maps onto the NetworkX API is called degree centrality, right? We calculate degree centrality by taking the number of neighbors that a node has and dividing it by the total number of neighbors that a node could possibly have. And the definition of the number of nodes, that number of neighbors that a node could possibly have, is dependent on whether you have self loops allowed or not. In the NetworkX API, self loops if I remember correctly, self loops are not by default allowed, or not by default considered, right? So your denominator is always number of nodes in the graph minus 1. So network X does provide a degree centrality function. The way that you use it is you use nx.degreeCentrality, pass in the graph object G. I'm going to do this step by step, actually. And what you get back is a dictionary that maps node to degree centrality metric, which then, if you know the patterns that we're trying to establish, you can pass that into a pandas series and do stuff like rank ordering and the likes, okay? So that is one thing that you can do here. Again, if we sort the degree centralities pandas series by in descending order, we should get the exact same order of nodes, 51, 272, 235, 195, et cetera, et cetera. So what we're going to do next is we're going to make a plot of the degree centrality metrics. Every node has a degree centrality entry. So if you consider all of the nodes, you get a distribution of degree centralities. Let's talk about how we might plot this distribution. I'll explain why the distribution matters later, but let's first talk about how we would plot it. If you have a distribution of values, what would you use? What would you canonically reach for? Histogram. And let me see. 2015 was when I learned about ECDF. So pre-2015 me would reach for histograms as well. But in 2015, I learned about a different kind of distribution plot that blew my mind, and I would like to share that with you. And it's called the Empirical Cumulative Distribution Function. How many of you have heard of this one? Cool, awesome. Those who have heard about it know how awesome the ECDF is, but also know how unfamiliar most people are with the ECDF, right? So here's what the ECDF is. On the x-axis, you have the values that are present in your data set, and on the y-axis, you plot the cumulative fraction of data points in your data set that are at that value or below, all right? And that is another way, that is an alternative way of visualizing the distribution of values. So if you do inside here, we have, inside this next exercise, we have a function called ECDF that will return exactly the values in sorted order and the cumulative fraction that you need to be able to plot. So what I'd like you to do first is attempt the exercise, probably 2 to 3 minutes, and use that to plot the degree centrality distribution. I will then explain, once we have the degree centrality distribution plot up, why ECDFs are so awesome. Okay, cool. So let's take a look at what's going on over here. I'm going to first explain the ECDF. Then I'm going to explain why visualizing the distribution of some metrics of a graph is really important. First off, let's take a look at the ECDF. You have, on the x-axis, like I mentioned, all the values that are present in your data set. And then on the y-axis, it is the cumulative fraction of data points that fall within, that have a particular value or less, okay? On the right, I've done the exact same data set, the distribution of degree centralities, except done as a histogram. And immediately, it should be clear that the histogram can hide information about your data set that would be otherwise exposed immediately with the empirical cumulative distribution function. So first off, have a question. Are there, if you looked at the histogram, would you be able to know if there are repeat values in your data set? No. Can you tell if there are repeat values in the ECDF? How so? Yes, you have vertical bars of data points, right? Second thing, from the ECDF, from the histogram, can you tell what the median 25th percentile and 75th percentile values would be? Completely impossible, right? On the other hand, you can very quickly guesstimate what the interquartile range might be. If you want to know what the 25th percentile is, draw a line from the y-axis at 0.25 until you hit the ECDF, and then draw a line down to the x-axis. You get the value there. If you want to know what's at 50%, you draw from the median, right? You go from 0.5 and draw down. Same thing for the 75th percentile. You can do any arbitrary percentile. That's my point, okay? So you can very quickly read off arbitrary percentiles from ECDF. You can't do that with a histogram. Thirdly, can you tell if there are outliers, potential outliers from a histogram? No, completely impossible. On the other hand, 3 points show up immediately as potential really outlier kind of things, right? So I hope at least these 3 points communicate to you that it is very easy to either intentionally lie or unintentionally obscure information that is important about a distribution by using histograms. On the other hand, you have a lot more information that is immediately gleanable from an ECDF. Final advantage. How many of you have tried plotting 6 histograms on top of one another? You can plot 6 curves very easily. You can't do the same for histograms, right? Question?
I hadn't seen that graphic line outlier. Why would anyone use histograms? Do you have an answer to that?
People are attuned to area and height. And so if we want to know where the maximum is, place of maximum density is, it's easier to visualize that in a histogram. It's harder to visualize that in an ECDF. That is perhaps the one place that I would concede that a histogram makes a lot of sense. But in that case, I would still preferably use, instead of a histogram, I would do the 1 unit diff of the array of values here and plot that as the approximation of the density, right? Because the ECDF is actually the empirical area under curve of a histogram or of the empirical distribution. Question? Outlier? Outlier means things that don't appear to look like they come from the rest of the distribution. So in this case, there are 3 points that lie way out, right, compared to the rest of the distribution, which looks really nice and tight. There are some distributions that can generate potentially arbitrarily looking like things that look like outliers, but they're actually part of the distribution. So we have to be careful about calling them outliers. Yeah, so I'm just going to leave it at that for now. Cool. Any questions on this point? This is like a slight detour around visualizing distributions. Visualizing distributions is really important, right? Because there are ways to generate, processes that we can imagine in which graphs are generated, and they will give us different distributions of things like degree centrality and other centrality metrics. So imagine we have some data that is our current degree centrality metrics, right? There is a process of generating a graph whereby you initialize a pool of nodes, and with a certain probability, you say that nodes should be connected to one another, right? So you draw like 0.1, 0.1, 0.1 coin flips for yes, no, these 2 nodes should be connected by an edge. That process generates a different distribution of degree centralities. There's yet another process called preferential attachment, in which you start with a bunch of nodes, and you start off by picking any pair of nodes at random, and you do a coin flip to ask, should they be connected? That is your seed edge. Now, every subsequent edge that you introduce into the graph, every subsequent node that you introduce into the graph, you can draw a biased coin flip that says it should be attached to something that already has an edge versus something that does not have an edge already, right? So that will give a different distribution of degree centralities on the graph. So if you know the characteristic distribution of degree centralities for certain graph generating processes, you can actually check to see whether your graph of interest was probably generated by that particular process or not, right? That is one way of answering the question, what is the underlying process by which our graph was generated, okay? So that is one of the things that I wanted to emphasize by introducing this idea of degree distributions. That is, different graph generating processes have different characteristic patterns in their degree distributions. Any, yes? Yeah, there is a paper by a Northeastern professor, Albert Laszlo Barabasi, right? And I think this was a year, thank you, Myrtle, 1999. He published this in Science, I think. And if you look up that article, there he makes the case for a graph that he named after himself. No, I'm joking about that. I actually don't know where the name of that graph name got associated with him as a result. And it has its own sort of characteristic distribution of certain metrics as well. Degree distribution is just one of those, right? There are other characteristic distributions you can plot. Okay? Yeah, that's right. Cool, thanks, Myrtle. Cool, let's move on. Now, we're going to skip a few exercises because those can be sort of exercises that you can do at home. What we're going to do here is we're going to plot the circles plot of this graph and do a little exercise in visual analytics, okay? So we know that this is an exhibit, right, of people moving through the. This is a great data set of people moving through the exhibit and asking whether they had face-to-face contact, right? So we're going to plot here two views on the graph. One is the Circos plot, and one is the arc plot version. The nodes happen to be ordered by the time in which they entered into the exhibit. Studied, for example, the arc plot or the Circos plot. You can look at it either or on your laptop. What can you tell about the pattern of connectivity that is happening inside this exhibit?
It happens during short intervals.
Yeah. So there seem to be people. Can you explain a little bit, actually?
Yeah, so there's a density, like in tightness on the x-axis.
Yeah.
Little
Cluster. Right, absolutely. And I agree with that. That means a lot of, if you squint hard enough, you see something like over here, over here-ish, maybe overlapping a little bit with the next one, and then over there, right? So that means a lot of connections were local. Cool. What else? That's the big, broad brushstroke structure. What about something that is special or unusual that you might see?
It looks like there's a big arc there in the first third of the graph. Like, why are those people connected?
Yeah, that's a really awesome question. Exactly. So if we notice that most of the connections are kind of local and clustered, what's up with these big ones? So immediately, looking at a rational plot gave you the hint of a next question that could be answered. I don't have the answer, unfortunately, but it is a very, very awesome example of we did the plot in a rational fashion, and therefore we have that immediately pops out the next logical question that we might want to go and answer, right? Try fishing that question out with a hairball. You would not, all right? Cool. So that's the visual insights thing. We're going to stop at this point on this notebook because it's 11 and I want to make sure there's enough time for a bio break. So I wanted to reflect a little bit very quickly before we go for the bio break. This is the first example in this tutorial that shows how the structure of a graph, that is the edges that connect nodes together, give rise to something that's interesting about the nodes, right? Nodes that are connected to lots of people would be something of potential interest to look at. You can imagine the utility of identifying the high degree centrality nodes in a network in many situations. If you're trying to amplify a message through social media, you want to get through to the celebrities on social media who are connected to lots of people. If you're trying to find the super spreaders in a network, right, as was done, say, for example, during the HIV spread in the 1990s, right? Super spreaders were identified by looking at who had the most number of contacts with other people, right? This is another application of using the degree centrality metric, or the number of neighbors that is inside there, inside a graph. So this is, again, the first one. In the second and the third notebooks, we're going to figure out other ways in which the graph edge structure gives rise to more interesting stuff. So we're going to take I think we generally need like 9 to 10 minutes for breaks. So let's come back at 11:10, and then we'll continue on with the next notebook. Alrighty, in the interest of time, we'll reboot. Let's get started. So this time round, we're going to run through notebook 02, we're going to run through the paths notebook, which is under 02 algorithms / 02 paths.ipynb. So I'd like you all to open up that one. In this notebook, we're going to encounter the most challenging exercises of the tutorial. So brace yourselves for a little bit of like brain work, probably about 10 to 15 minutes worth of coding time, pair coding if you want. We're going to actually see how to think on a graph, pretending that we are a dumb computer that doesn't know how to just see the structure of a graph, right? So when we think about the structure of a graph, one thing that's really cool is we can actually start figuring out whether two nodes are connected implicitly to one another, even if they are not like directly connected to one another. And that involves reasoning about paths through the graph, right? You jump from one node to the next, to the next, to the next, until you hit your destination node of interest. It's kind of important if you're thinking about routing stuff through a transportation network, for example, right? And you want to figure out what is the shortest path that you need, that is available, given that you go from this to the next place, to the next place, to the next place, and so on and so forth. So what we're essentially going to figure out in this notebook is how to think like a computer when trying to solve for whether two nodes are connected inside a graph by a path, right? If you think about it as a human being, we put a map of all the nodes up on a matplotlib canvas. You can sort of just look at the graph and go, yeah, this here, there, right? And then you're done, and you've got your path. But if you want to programmatically solve that problem over and over and over, you can't rely on a human to use their visual cortex and go, yeah, right? Like that doesn't work for scaling up the problem. You need a programmatic way of handling the problem. And that's where we're going to introduce in this notebook the breadth-first search algorithm, which is commonly taught in lots of computer science curricula. How many of you have ever implemented it before? Quite a number of you. So if you're familiar with the algorithm, treat this as like a refresher. I remember when in 2015 I was trying to work through the breadth-first search algorithm, it took me at least 3 attempts with an MIT undergrad to figure out how to do it correctly, right? And we made lots of mistakes along the way. So for those of you for which this is the first time that you've ever encountered the breadth-first search algorithm, just know that I have 0 expectations that you'll be able to finish the exercise that we have, which is to implement the breadth-first search algorithm. I have 0 expectations that you'll finish it within the 15 minutes that we're going to allot, because it took me at least three attempts of whiteboarding whiteboarding each session being an hour long to figure out exactly what to do, all right? But what I hope this does illuminate, however, is this concept of thinking on a graph, where now you're not just relying on intuitive visual cues to figure out how to solve a graph problem, but you're really starting to reason step by step algorithmically what needs to happen on the graph in order to solve your problem. Why is Siri doing stuff? Okay, cool. Alrighty, so what we're going to do is sort of a two-step thing. We're going to first, for those of you especially who have never attempted the breadth first search algorithm, I'd like you to find a way to take a piece of paper or take a text editor of some kind on your laptop and write out what you would need to do step by step to solve the following problem. I have a starter node, I have an end node, and I want to figure out whether there is a path to be able to go from one place to the next, one node to the other. That will involve using a breadth first search kind of algorithm inside there. So I'd like you to spend maybe about 5 to 10 minutes jotting notes, talk with your neighbor. Now that we know the formal definition of a neighbor, talk with your neighbors about the problem, how you would solve it, and even better if you can, try drawing out the steps algorithmically on a sheet of paper. If you can't, use a text editor as your aid. All right? Give it a shot. Alrighty. Okay. I hear the discussion subsiding a little bit. Just now I had a flash of inspiration, and I think it's valuable to talk through what was difficult about this problem, right? Because from there we get to learn a lot about where the struggles are that may be common for other people that I have also probably have gone through as well in trying to understand how to think on graphs. So I guess the first question that I have for everybody was like, generally speaking, what was the difficult thing with respect to, what did you all find that was a key conceptual blocker in trying to design a breadth first search kind of algorithm?
For me, and I just went through this a couple months ago, but understanding the queue implementation of a list as opposed to the stack implementation. So on top from the left.
Yes.
And from the right.
Yes. Okay, so that is one very important thing, right? So when you have a queue, basically what we're trying to do here is we want to be able to, a queue is a key data structure that is needed to solve this problem. And what is the queue used for in this case?
So the queue is used for all of the neighbors for the node. So if you want to do breadth first search, you want to go through all the neighbors before you move on to the next thing. So you pop a neighbor, you grab all the neighbors of that one, run it to the end, and then grab the next one and so on.
That's right. So you need to keep a running queue of things that I need to check, right, as you go on. And understanding that we can, in a Python list, you can actually grab from the front while also appending to the back, right, is a very important concept that maybe not all of us are very familiar with, right? So that is kind of a very important key thing to recognize. So that's a cool one. What else was difficult?
I mean, if you had used a stack instead of a queue, then you do depth first search?
I think so, that's right. I have to admit, I don't have depth first search in my working memory right now, so I'm going to trust that is the right thing to do. So if you used a stack, you probably would end up writing DFS rather than BFS. Anything else? What else was difficult about the problem?
I think it was hard to start with a case.
Yeah.
You might want to start with a tree because a tree is you arguably say is simpler.
Yep.
And so that it's kind of simple.
Yep.
But then, in my mind, I run into the issue, which is how you reconcile what you have visited versus what you're going to put in the queue next.
Yeah.
As it relates to recursively traversing through.
Yes.
And then once you've gotten through that, then you do a more generalized version of the graph, which is not a tree.
Yep. Yep.
And then you run into other issues there.
Yep, absolutely. So one thing I like about this response is that coming up with a minimal complex example is an incredibly challenging thing to do. But once you develop the skill, it takes practice, but when you develop the skill of imagining minimal complex examples, things that capture the essence of the complexity of the problem, but aren't too big that you can't reason about things in your head, that is an incredibly useful skill for solving computational problems more generally. And when it comes to graphs, coming up with graphs that look complex enough, like developing a taste for graphs that look complex enough but aren't too complicated that you can't reason about it in your head, is incredibly challenging as well. For that reason, I asked in here that you conjure up a graph of maybe about 15 to 20 nodes, which seems to be about the right level of complexity. You can, for example, try to implement breadth first search on a chain graph, which is just one node connected to the next, connects to the next, to the next, and that would be too trivial. You would not have learned to solve edge cases in trying to solve breadth first search with a chain graph. But if you set up something that had like a cloud of 15 to 20 points, and you randomly connected them together, and you just fixed your eyes on that graph for a moment, and then started to try to reason through how you would create the queue, how you would populate the queue, what sort of things you would need to have to happen, what kind of conditional logic you need, right? Like you don't want to revisit nodes, right? That is another one that is troublesome. So if you end up revisiting node, that's not good. So you need to bake logic in there as well. Coming up with that minimal complex example is incredibly useful for solving computational problems. I remember at work just last year, we were solving, again, graph-related problems. And they were related to nucleotide sequences and how they were supposed to be assembled together. And we spent roughly 2/3 of the time solving this problem by coming up with an example that was small enough for us to reason about, but also representative of the complexity of nucleotide sequences that we would ever see at work. So it was the bulk of the time. It's almost like when developers spend the bulk of their time writing unit tests first before really figuring out what the implementation is. In this case, for data scientists, figuring out the minimal complex structure of the problem before going to solve the problem is where it's really useful. So I love that answer. What else? Was anything else that's like challenging about the problem? Okay, so I'm going to leave you all with what I believe is the one correct answer for BFS, or one of many variants of, not variants, permutations of letters that would give you the same BFS algorithm, right? As I mentioned, it took me a few tries to get it right. I'm going to leave this as something that you can take home and try to re-implement for yourself if you've never done it before. Once again, I'm going to emphasize that it is really valuable to be able to think on graphs, and the breadth first search or depth first search algorithm, right, figuring out that implementation and then writing it in code and then actually seeing it work is extremely validating for your ability to solve graph-related problems. And mark my words, I've experienced it before. When you have the skill of solving graph problems, suddenly a lot of things look like graph problems, and they become solvable when they initially may not have looked solvable, all right? Cool. So we're not going to actually implement the algorithm over here. And the reason I said this was the most complicated exercise in the tutorial is for exactly that reason. Now, it's also from the perspective of, like, did we even need to do a breadth first search algorithm? No, because that is baked into Network X. And if you wanted to solve the path exists problem, Network X actually has a function called shortest path, which will implicitly give you whether a path exists between two nodes or not. All right, so pardon me. So you don't actually have to know how to implement the breadth first search, and you don't actually have to implement the breadth first search over and over in your own work.
So is the shortest path doing only breadth
I think it is breadth first search underneath the hood. Mriddle, do you remember? Mm. So yeah, so just to repeat the question for YouTube later on, what algorithm is nx.shortest path using? Mriddle's answer is basically it depends on the graph, and you actually can configure, I don't think you configure the function, but you actually call on an explicit particular network X function to find the shortest path using a particular algorithm, whether it's DFS, Dijkstra, shortest path, etc. So you wouldn't configure nx.shortest path. You would import nx and then nx.Dijkstra shortest path on the graph between two nodes. All right? Cool. Awesome. Anything else? Any other questions so far? All right. So yeah. So implementing breadth first search to find out whether a path exists between two nodes is completely unnecessary for solving the problem, given that network X has already solved the problem for you, which is kind of the point of having a software library that you can import and rely on. So if you do nx.shortest path of, did I forget to import something? So if you import network X and you do nx.shortest path, you pass in a graph and two nodes, what it will do is it will return for you one shortest path. And this may not be the only shortest path that exists between two nodes. There could be multiple shortest paths. It will return one of them for you. What's really nice then is you can use this to figure out the length of the shortest path, right? The length of the shortest path in this case would be 1 hop, 2 hop, 3 hop, 4 hop, 5 hops. You need 5 hops to go from one node, node 7 to node 400, okay? So far, so good? All good? So you can then use this to sort of understand the structure of the graph. Now, if you wanted to visualize just this little portion of the graph, there is actually a way of creating subgraphs from a graph by doing g.subgraph of a collection of nodes. And what that will give you is the nodes that only belong to that subgraph and how they're connected to one another. So if you wanted to visualize just this path, right, we could do this set of class method calls. You do little g is big G.subgraph of the shortest path between those two nodes. And then we might, for example, plot a matrix plot of all of those nodes together. And you can see that this has the characteristic signature of a chain graph, where you have nothing on the diagonal and stuff on the one-off diagonals, all right? And if you wanted to, you could also rely on network X's built-in drawing functionality and see that this is indeed a chain graph as well, okay? Okay, if you tried, now notice that because the subgraph it's not inherited, but it's sort of like we're isolating a smaller part of this bigger graph when we do a subgraph, right? So as a result, that subgraph is not mutable. It is completely immutable because we're assuming that the bigger graph is the one that we're caring about, and we're sort of isolating just a little section of that bigger graph. So you can't actually add in nodes into a subgraph, right? That is a very important thing to keep in mind. In network X, I think this is called a frozen graph, right? Okay, so one of the things then that we might want to do is grab out the chain graph of interest, but also visualize stuff that are 1 degree of separation off nodes on the chain, right? This gives us a little sense of the context of the chain, the local context of the chain in the broader graph. So here's an exercise for us to attempt, which is to draw the paths with, draw out the, to be able to visualize the graph, the path that we have, but also all of the nodes that are 1 degree of separation out from every node on the chain on that path, right? So I'd like you to try to attempt to solve that problem. You have all of the API tools that are needed to solve this problem. Okie dokes. So in the interest of time, I'll walk everybody through the solution. Of course, with the knowledge that we always can go back and try to attempt the exercise on our own time, all right? So the first things first, we know that we want to collect not only the nodes that are along a path, but also those nodes' neighbors at the same time. So what we can do is we can initialize a list that contains nodes on the path, and then as we iterate through nodes in the path, what we do is we append to that list or extend that list with the neighbors of that particular node. So that is what we're doing here. So we instantiate the nodes of interest with just the nodes in the path first, and then we iterate over the path, grab out all of the neighbors for each node, and then we extend the node of interest with those neighbors. Now, you might have realized, as I just did, that the better way to handle this is with sets if we really wanted to guarantee that there were no duplicate additions of neighbors into the list, right? So if we do that, we might do this, and then we might do node of interest equals node of interest dot union of neighbors. I think that should work. And yes, it does, and we get the same solution. For effect, I'm showing again the hairball. You kind of can glean where the path, the chain graph looks like, but it's not perfect. So in the official solution, we use NXViz to plot the path with neighbors, and we use a little bit of the highlighting capability in NXViz to highlight particular edges that correspond to the original path, and then the rest of the edges show sort of the local structure around that path. Any questions about this? Seems okay. Basically, the thing that I wanted to get everybody to get practice with was the g.neighbors API, as well as the g.subgraph API, all right? And this hopefully was a bit of exercise that helps with that. Now, why are we talking about paths? Well, not only are paths important for routing, but also paths through a graph can lead us to this next very important concept, which is this idea of bottleneck nodes. If you have information flowing on a graph, one way of, well, okay, let me step back a little bit. We were talking in the last notebook about nodes that are important because of the edges that exist between them and their neighbors. So nodes that have a lot of neighbors, they may be considered really important. Now, there's another way of assessing node importance, and that is asking, if I were to remove a node, would information flow on the graph be disrupted severely, right? And one way of figuring that out is asking the question, how many shortest paths flow through a particular node, right? If in a graph we have a node that is really, really important, in the extreme case, it is the only node that bridges two sort of subcommunities. If you remove that node, those two subcommunities are going to be completely disconnected. So that node somehow has a lot of importance, but it may not have a lot of neighbors, right? So that's a really important thing to keep in mind. So paths give us another definition of importance of nodes. That is, what we call this is the Betweenness centrality metric, right? And what the Betweenness centrality metric measures is how many shortest paths run through a particular node relative to all of the shortest paths that could exist in the graph, all right? That is the Betweenness centrality metric. What's up with Siri? Gosh, never mind. I'm just not going to wear it. Cool. So the betweenness centrality metric in network X is provided as a function, and it is just like the degree centrality metric. So if you think over here, we can calculate the degree centrality for, betweenness centrality for every single node in this graph. Now, one thing that we can do is, let me see, where are we? We can actually plot and compare how degree centrality and betweenness centrality might look like. Now, having not shown the answer just yet, what are some of your priors? Do you expect them to be well correlated, even if not perfectly correlated? Or do you expect them to be not necessarily correlated at all? Not necessarily would be my prior as well. So if you were to attempt the exercise, you would get something that looks like this guy over here. I skipped over the exercise in the interest of time because I want to make sure we have time to address some of the more advanced things that others have asked about in this tutorial. So you can see then that degree centrality and betweenness centrality do not necessarily have to correlate with one another. I mean, if you were to zoom in hard enough and restrict your view of betweenness centrality to just 0 and 0.05, you might see a bit of a y equals x kind of scatter plot, but you know, that's a very tentative way of looking at data. Please don't do that. Like, please don't. Okay, so now if you think about the situations in which degree centrality and betweenness centrality may not necessarily correlate, this is the exact example that we were talking about just now. It's a special type of graph. It's called the Barbell Graph, just because it looks like a barbell. And what it highlights here is that you can have a node that has a very low degree centrality because it's not connected to very many things, but it's got such a high betweenness centrality because information to get from this community to that community must flow through that one little node there. So if you remove this guy, the two become disconnected. You can imagine less extreme situations where you might have two paths, right? And if you disrupt, so you might have a second node over here that stuff can also flow through, but then they both would have really high betweenness centrality. So if you remove one, you really increase the load on the other, right? And that's a really important visual. For me, this is the minimal complex example that highlights why degree centrality and betweenness centrality do not necessarily have to be correlated with one another, all right? Any questions on this thus far? All right, let's see. I am going to make a call that we do an early bio break for 8 minutes till noon, and then we'll come back and we'll talk about the linear algebra and data I/O notebooks, all right? So let's go for a bio break for till noon, and then come back at noon for the final 2 notebooks. Yeah.
Is there like an internet?
Test, test. All right, we're good. All right, final 20 to 25 minutes of today's tutorial. We're going to let our brains relax. I'm going to provide all the entertainment. It will be primarily lecture style, but please feel free to ask questions along the way, all right? This is how we keep the so-called lecture style portion a little bit more interactive and entertaining that way. A lot of the times we get questions about like, okay, yeah, you've given us a graph object, but how exactly do you load that data in? And we sort of kind of addressed that question early on in the tutorial, but today, but in this notebook, I actually want to address this question head on. All right, so let's see here. In this notebook, what we show is an example of how to load tabular data into Network X. Now, what's really important as a conceptual thing to remember is that your graph data, because it is a node set and an edge set, two sets of objects, you actually can represent your graph data as two tables, right? And if you think about what's going on in a database where you have a relational database, that is almost kind of a good anchoring example that you can use to reason analogously about what's happening inside a graph table, all right? So you have, to represent your graph as two tables, you need, firstly, the node table, which is indexed by node ID or node unique identifier and has as columns the metadata that are associated with the nodes. And then you need the edge table, which has as sort of two indexing columns the two nodes identifiers that are present inside the that comprise each edge, and then columns of data that represent the metadata that's inside there. And I'm going to show you an example of this with down here. First off, we're going to go through a simple example, and then we're going to walk through a slightly more complicated example. So if you were to have a graph that has 3 nodes inside here, you could have them as a plain text file in which one line is one node, right? You have the node set, node list, for example. And if you had metadata, you could tag it out. You could do like a comma-separated file that looks like this guy, right? And the same can be said for edge sets, right? You have one row is one edge, and if you had metadata that's on top of it, you can represent it in a CSV format too. So, and then if you really wanted to, you could construct a combined representation that has both the node and edge metadata inside there. By definition, you're going to end up with a lot of duplication of information, as you can see over here, right? N2 is, in this place, we have CC in N2 and an N1 over here. So you see the shape1 num1 and shape2 num2 being duplicated across the rows. That is a convenience, that is the price of convenience. You get a lot of duplication in your data. So the most compact representation is actually the, what do they call, fully normalized in database land, right? They have the normalized tables where you have just the node information and just the edge information, and they're not combined together, all right? But this is also possible. So now, that was a toy example. Here's an actual example where we do the Divi bike sharing data set. And this was a public bike sharing, ride sharing data set. Inside there, from the city of Chicago, inside there, what they have are stations and trips taken between stations. The edges are actually unique trips. What I've done inside this notebook is just to collapse them into number of trips. All right, so this is mostly a convenience thing. So as you can see over here, let me just run through things a little bit. This is the node table as a CSV file, now as a pandas data frame. And down below here is the trips table, which I'm going to, which is the summary table that we're going to work with. And this says from station ID to station ID, which is pretty much analogous to your edge, right? From node to node. And then in this case, we have metadata, which is number of trips. So that is to say, how many trips occurred between these two stations within this time period. Any questions at this point? So I hope this is like kind of clear, right? There's nothing complicated, fancy like breadth first search going on. There's no math, linear algebra going on. There's no deep database theory going on. It is literally, I have nodes as a table and their metadata as columns. And I have edges also as a table, and the columns of information that are metadata are also stored inside there. All you need to have is the unique identifiers correctly placed in each table, okay? So then, now how do we load that in as a graph? So NetworkX does have function called from pandas edge list. And that's what this does for you is it gives you the ability to specify what the source column and the target column should be, as well as what the edge attribute should be, like which columns constitute edge attributes. And underneath the hood, it will automatically create the graph object for you. So we can do, for example, nx.info on G and print out how many nodes and edges are present inside the graph, and take a look at this guy over here, which is to say that, which gives us the edge table, except now represented as part of the NetworkX graph object, okay? So this is all really, really useful. Notice, however, we don't have any of the node metadata that are present, right? And that's because when you add nodes into a graph from the edge list, you by definition don't have any node metadata. So what we need to do then is we need to annotate the node metadata afterwards. So if we wanted to, for example, add the name, the latitude, longitude, the capacity, landmark unique identifier, and the date at which this thing came online, then what we would need to do is loop over the node table, grab out the metadata that we want, and add them as key value pairs inside the graph, all right? So there's no automatic way to handle the node metadata just yet, but the edge metadata is automatically handled, all right? Questions at this point? Okay, looks like it's all pretty pedestrian, right? Like there's nothing, like I mentioned, no fancy math, no fancy concepts involved here. Most of it is brute force data processing. You can write a for loop. You can do almost anything you want programmatically, all right? Cool. One of the things that we do inside this notebook, which I'm not going to harp on too much, is that we can filter the graph for particular properties. So, sorry, like if you have edges, if you have a graph like this guy over here, and you wanted to plot only, say, the edges that had 100 trips or more between bike stations, then by necessity, we have to filter the graph and get rid of or not consider edges that are less than 100. So there's an exercise inside here that lets you filter out edges that, for which the ask is to filter out edges that are that have a count of less than 50 trips that are present inside there. And then you can take advantage of the geoplot capabilities of NXViz to make a visualization of the graph, right? The geographic spatial graph inside of this data set. And you can see it probably has that like Chicago kind of layout that you would expect. However, I'm going to caveat this by saying you probably do want to use PySal, which is for a spatial analysis library for Python to do more concrete, more complicated or more principled analyses of geographic graphs, right? That's what I would recommend. You can use NXViz for quick and dirty views, but go to PySal if you want to do anything that's serious with geographic networks. Okay, cool. And then the final thing about graph I/O that I think is important is that because NetworkX graphs are Python objects, they are pickleable, which means you can dump them to disk and then reload them on another place. Doing so comes with all of the caveats of pickling, right? So if you know all the caveats of pickling are, they're basically, you need to be able to trust that the pickle does not contain malicious code that will automatically run on your computer, right? So don't do this unless you're in a real pinch. Riddle.
These bit of lines would be removed from NetworkX in the next release, or we will not use this.
Okay, this is good. This is good. So I'm actually going to, so in the next release, we're actually getting rid of write gpickle and read gpickle. Yeah, that's like, this is good because like NetworkX, the library, is reintroducing friction into the processes that should not happen, right? So like we make the right thing easy to do and the wrong thing a little harder to do, so you don't do it as often, right? And slowly that friction should build up and you don't end up pickling graphs. But if you really needed to, okay, fine, just do it, right? Cool, and that's it for this notebook on Graph.io, right? It gives you one example of how to read data from a text file and turn it into a graph. Key concept is node table, edge table. Node table, edge table. You remember these two things, even if you forget the exact API calls, you'll still be able to repopulate and create a graph, NetworkX graph object in memory, all right? Cool stuff? Awesome. We're gonna skip over testing. Yeah. Yeah.
So it would be impractical to do this. I would probably want to store it all in a database.
Probably.
And going about that. I mean, one could use SQL, right? But I don't know that it would perform well.
You don't know that it would, sorry?
I wonder if it would perform well.
So performance depends on what you mean by performance. I think if you were to do the initial graph creation in NetworkX and you were talking about like tens of millions of people in the social network, at that scale, don't use NetworkX, right? Use cuGraph, for example. cuGraph being the rapids. I'll flash up cuGraph, actually. It's a pretty cool package. So NVIDIA naturally has a vested interest in writing GPU-accelerated algorithms for the Python community. So they invested a lot of manpower, a lot of resources into building out the Rapids package. So if you look for Rapids AI NVIDIA, that will give you access to essentially the Python data stack, or as whatever it could cover of the Python data stack accelerated on GPUs. So cuDF for Pandas data frames on GPUs, cuGraph for NetworkX on GPUs, and so on and so forth. There's like a whole ecosystem of stuff that they've built out. At that scale, we would want to probably defer to cuGraph. Potentially, actually. So if you explicitly wanted to keep node metadata and edge metadata, then actually, so data frames being one way of doing the thing, graph databases being the alternative. And yes, Neo4j plus a whole suite of other open source alternatives that are out there as well could be viable solutions. Cool? Okay. Cool. So we're going to skip over bipartite and go to linear algebra. I found this one fascinating and mind-blowing the first time I encountered the connection between linear algebra and graphs. So what I'm going to do here is I'm going to run the entire notebook first and talk a little bit about 3 key ideas that we can represent using linear algebra methods. The first is pathfinding. As it turns out, you can do pathfinding if you know how to take powers of the adjacency matrix, right? That's the first one. The second one is message passing. Message passing happens if you know how to do dot products. And the third one is something that touches on a notebook that we've skipped, but I will explain the key idea. If you have a bipartite graph, that is nodes that have 2 partitions that are never connected within each other and only connected across partitions, then you can actually create the projection of this bipartite graph, that is, how nodes of one partition are connected with each other based on their connections to the other partition. You can create that partition simply by doing linear algebra, all right? So let's go through the first one, which is pathfinding. For pathfinding, let's say we have a chain graph over here. Now, I did mention chain graphs are really bad for like minimal complex examples, but in this case, any more complicated than a chain graph, and it really does get really hard to reason about pathfinding with linear algebra methods. So if you have the chain graph that looks like this, you can obtain the adjacency matrix. The adjacency matrix is obtained as such. Adjacency matrix of G1. And what you get here is a sparse, SciPy sparse matrix. I believe if we import NumPy, that didn't work. Myrtle, can you help me with this? Is it too dense? Thank you. You get the NumPy array version. Ignore the fact that it shows matrix. That API, I think, is being deprecated. You really should just be using NumPy arrays. So you can see the chain structure in the adjacency matrix where there's nothing on the diagonal and stuff on the one-off diagonals. And then that is also visualized inside the matrix plot. Oh, well, OK. What did I do? I did this. To NumPy array. Sorry about that. So there we go. So when we do pathfinding, one of the things we want to be able to answer is whether two nodes are connected to one another, right? As it turns out, if you use the adjacency matrix and you take linear algebra matrix powers of the adjacency matrix, you can answer a related question, which is how many paths of length k, which is the power, exist between two nodes. So let's show that. So A1 is the graph of, the adjacency matrix of our graph, of the chain graph. If I take the second matrix power, so raise it to the matrix power 2, here's what we get. You get a diagonal of 1, 2, 2, 1, and then an off diagonal, one off diagonal of zeros, and then a two off diagonal of ones, and then a zeros at the corners. So what's the interpretation? In here, we're saying there is only one path to go from node, that first node, back to itself in 2 steps. For this guy, there are 2 ways to go from that middle node and back to itself in 2 steps. Here, there's 2 ways as well. And the final terminal node, there's only one to go back to itself in 2 steps. And then, so things that are 1 degree of separation away, by definition, you can never go from one node to its neighbor in 2 steps. Like you try to do it, like you either go 1 over or you go back, right? There's no way to go to your 1 degree neighbor in 2 steps. That's why this is 0. Then you do that over there. There's only one way to go from something from one node to a 2 degree neighbor in 2 steps, right? There's only one way to do it. And there's no way to go to a neighbor that's 3 degrees away in 2 steps, 0 ways. So that's the interpretation of this first like power 2 matrix. What do we do here? So if we do a third matrix power, notice how everything here becomes 0 on the diagonals, because there's 0 ways that you can go from a node back to itself in 3 steps, 0 ways. You can try to work it out in your head. There is only one way of going from a node to something that is 3 degrees of separation in 3 steps, and that's the matrix power. So you can imagine then, if you wanted to figure out a brute force way of using matrix powers to figure out whether there's a, if you wanted to use a brute force way to figure out whether there is a path between one node and another, do consecutive matrix powers, which is cheap, right? Fast to do at least, and see whether the entry between 2 nodes ever is non-zero. If you ever get a non-zero entry, you know that there is a path from one node to that other node, right? That was mind-blowing. Matrix powers. Matrix powers, okay? Same can be said for directed graphs. The interpretation is identical. It is how many ways are there to go from source to sink in k power steps, right? So if you do k to the power k is equal to 2 over here, there's one way to go from this node to stuff down 2 degrees of separation. But because there's directionality in the edge, there's no going back, right? So there's actually 0 ways on the diagonal over here. There's no way to go from one node to the neighbor and then back on the directed chain graph, which is kind of cool. All right. Next up, message passing. Message passing requires 2 matrices. You need to have the adjacency matrix, and you have to have an indicator matrix that asks where the message is on the graph. So the indicator matrix is sort of like the node it is a length number of nodes, and it has a 1 where the message is indicated to be present on that node, and 0 everywhere else, okay? So if you do the message matrix dot product against the adjacency matrix of, say, this directed chain graph, take a look at what the result is. You actually get the message moving from the original position to 1 position over. How does that work, right? Mind-blowing. And then if you do a dot product against the adjacency matrix again, you move the message twice over. Now, FFmpeg is where this comes in. I don't know if this will work, actually. Let's see. Does it work? Does it work? It doesn't work. Does it not work? No, it doesn't work here, but it will work on the website. You can visualize message passing. Let me just see here. Here we go. I want to make this full screen. That is what happens when you message pass and then reset the graph and message pass over again. All right, so dot product of the message indicator matrix against the adjacency matrix. As long as you get the array shapes correct, you do the dot product, you can simulate message passing on a graph. It's mind-blowing. Final thing we'll go through, bipartite graphs. Let me explain really, really briefly what bipartite graphs are. As I mentioned, bipartite graphs are where you have collections of nodes, and you have nodes that within each, you break them up into 2 partitions, and nodes can only be connected across partition. They cannot be connected within partition. And if you need an anchoring example, people buying goods. People are one partition, goods are another partition. We are hopefully past the era of people buying people, all right? So you only have people buying goods and not goods buying goods or people buying people, all right? So that is an example of a bipartite graph. You can represent that by what they call a bi-adjacency matrix. So I scroll down here. Rows, this customer product matrix, for example, is one where we have rows as customers, columns as products, and one is customer bought product, okay? So we have in here 3 customers, 4 products. If you want to figure out which customers are similar to one another based on shared product purchases, do a dot product. You take this matrix, this guy over here, dot product against its transpose, and you will now get a customer by customer matrix in which the diagonals show the number of things that they have purchased, right? And the off diagonals show between customer 1 and customer 3, they share only 1 purchase. Between customer 2 and customer 3, they share 2 purchases, and so on and so forth. The math works out.
That is insanely cool. I'm so sorry.
That was my exact reaction. That is insanely cool, right? Now, someone kindly put up a customer product graph from Amazon. And the bottom of the notebook, which you can review on your own time, shows how if you were to do what they call, sorry, let me backtrack a little bit. Doing this operation is called calculating the projection of a bipartite graph onto one partition. So we're projecting this bipartite graph onto just the customer partition. Or we do the same for onto products, okay? If you were to use Network X's thingy, let me just see here. Where do we show this? Performance objects versus matrices. If you're to use Network X's API to calculate the projection, on this graph that is however many hundreds of thousands of nodes, you might take a certain amount of time, like 15 seconds-ish. However, if you reframe the entire problem into linear algebra operations, half a second. So once you know the connection between graphs and linear algebra, primarily through the adjacency matrix, but also through other things, you get down a really fascinating performance and conceptual rabbit hole. Graph neural nets, for those of you who might be interested in neural nets that work with graph structured data, they have at their core the message passing algorithm that I showed you just now. If you're interested in like recommendation systems, they have deep connections to linear algebra. Like you can recast your entire graph problem in a linear algebra setting and obtain a lot of performance that way. On the converse, what's also really cool is when you start seeing matrices, you can't stop seeing graphs. Once you know this connection, every matrix is a graph at that point. And it just depends on whether it's symmetric or asymmetric, whether it is same number of nodes on each side, therefore, unipartite graph, or different number of nodes, then potentially bipartite, all right? So we're gonna leave us with that. I hope the last notebook that we showed was mind-blowing for you all, right? Just as it was mind-blowing for myself. Okay, cool. Keep in mind, all of the material are available online. Network Analysis Made Simple. It's freely available. You can run the code at any point on your own. If you want to get practice, you can always launch a binder session. If there's spare capacity, you'll be able to launch into it. Get practice with the code, get practice with the API. This world of graphs, network science, graph theory, etc., is fascinating. And I'm hoping that this tutorial has given you an awesome introduction to it. So thanks for coming, and we'll see you around PyCon.